Hello and welcome everyone to our workshop on versatile video coding, open optimized implementations. My name is Benjamin Bross from Fraunhofer HHI, and I'm happy to hold this workshop together with my colleagues Dr. Christian Helmrich and Adam Wietzkowski. What are we going to talk about today? We will start with an introduction and then dive right into the technical details of our VVC encoder implementation VVEnc, with Adam focusing on implementation and complexity, and Christian in the third section focusing on the subjective quality optimizations built in VVEnc. At the end, I will wrap up this workshop with an outlook and conclude it. In the introduction, we will now start easy with versatile video coding, and then I will introduce our open optimized VVC encoder VVEnc. Versatile video coding, or VVC, is a joint ITU-T and ISO-IEC project which has been completed in July last year. It's now an international standard, published from the ITU side as H.266 and as MPEG-I Part 3 from the ISO side. One main goal of VVC is coding efficiency, providing 50% savings over H.265 HEVC, which is the predecessor standard of VVC, emphasizing use for HD, UHD, and 8K resolution video with high dynamic range, wide color gamut, and 10-bit video. The other big part of VVC is its versatility for a wide range of application and content, but in this workshop, we will focus on optimized implementations optimized for coding efficiency. So the 50% bitrate savings over HEVC at comparable visual quality are achieved by many new coding tools that improve all parts of the hybrid video coding design, where a block diagram you can see here on the right side on the slide, which is the same basic principle since the first video codec standards H.261, MPEG-1, MPEG-2. But the new tools comes with new modes and new options, which increase the search space at the encoder that results in an increased encoder complexity. For the development of VVC, there's the VVC test model as a reference software implementation used for evaluation and verification of the algorithms and the bitrate savings. It shows a high coding efficiency, but software-wise, it is not optimized also with regard to fast algorithms. VTM version larger or equal than 10 represents the final VVC standard implementation. So for the coding tools, I would like to focus on one particular tool, which is the block partitioning in VVC. This is achieved by a quad tree plus multi-type tree, so QT plus MTT. It starts with a CTU, the coding tree unit, as a root for the tree. It can have 128 times 128 Luma samples, but can also be configured to be only 32 by 32, which can be used for speeding up the encoder algorithm, as we will learn later. So then there comes the recursive quad tree partitioning, or QT, as in HEVC, and nested in the quad tree leaves is a multi-type tree using binary splits, horizontal or vertical, or splitting it into 3 more partitions using horizontal or vertical ternary splits, as seen here in the example. And then it's recursive, so you can further split it again using binary and ternary splits. So the block partitioning has fundamental impact on all coding tools in a video coding standard. This particular very flexible block partitioning QT-MTT in VVC has the highest efficiency of all coding tools, but also the highest complexity. So there's a big potential for optimizations. When we now look at the overall coding efficiency performance, when we compare the VVC test model, VTM, with the HEVC test model, HM, under the JBED common test conditions for HD and UHD video. We can see that we started here at the beginning in VTM1, so the first version here, with an 11% bitrate savings, which is almost only contributed to the partitioning, and then we added up over the versions, resulting in 41% bitrate savings of VTM versus HM, but it also comes with an increased encoder complexity of 7.4 times the encoder runtime of the HEVC reference software. Decoder runtime is 1.6. This is quite moderate. So we have been monitoring this to make the implementation on the decoder sides and devices and chipsets very easy. But on the encoder side, there's a lot of room for potential improvements. When we compare the savings over HEVC HM with HEVC versus AVC after finalization of the HEVC standard, we can see that these gains of VVC are even higher than HEVC versus AVC at that time. When Christian will present the subjective results later, we can see that the subjective gains seem even a bit higher than that. So moving away from the VTM slow reference software implementation to optimized freely available implementations of VVC, this is where we at Fraunhofer HHI developed optimized software. This includes a versatile video encoder or VVEnc with the goal to have a fast real-world implementation while maintaining the high coding efficiency of the VTM reference software. In addition to that, we developed and released a versatile video decoder, which is also freely available on GitHub. The source code is available on GitHub since September last year, and since December 2020, it has a copyright-free clause BSD license to make it easy for everyone to contribute. So the current version is version 1.0 of VVEnc. It has 5 predefined quality speed presets, ranging from faster, so very fast, but moderate coding efficiency, to slower, having full coding efficiency when compared to VTM. The speed ups range from 16 times faster than VTM reference software to 1,040 times. All of these speed ups are achieved using multi-threading with 8 threads for UHD video. It also comes with real-world features as single pass or 2-pass VBR rate control. It has built-in subjective quality optimizations, multi-threading to increase the encoding speed, and framework-wise, it comes with a simple, easy-to-use C interface and has an expert mode with a VTM-style configuration interface for experts familiar with the VTM reference software. Also, when we look at the GitHub repository, we are happy to see first non-HHI contributors. So people are really looking into that and making use of it and also start contributing. So performance-wise, we have plotted here the preset curves of VVEnc 1.0. This is the solid green line on the right running single-threaded and the solid green line on the left running multi-threaded with 8 threads, compared to the HM reference software, the HEVC reference software here, and the VTM reference software here on the bottom right. So we can see that the slow modes can keep the VTM efficiency while being significantly faster. So the slowest mode is even faster than the HM reference software when using multi-threading. And then in the light green color, you can see the previous versions starting from 0.1 and how it evolves and got faster and faster over time, still keeping the high efficiency, so that multi-threading of the first version is almost close to the single-threaded version of the current version. So now we compare them with other state-of-the-art encoders that are freely available, for example, like AV1A or ENC3, this is the violet curve, or X265 version 3.4, which is the orange curve here. You can see that for both codecs, VVEnc at the same encoder runtime operation point provides higher coding efficiency in terms of AOM-enc or significantly higher coding efficiency in terms of X265. So this was the introduction. I hope I was able to build up what Adam is going to present now for the VVEnc implementation and complexity, which includes the profiling, the preset derivation, as well as some details on multithreading. And here I would like to hand over to Adam.
Hello, everyone. My name is Adam, and I'm gonna walk you through the more technical part of the talk. So let's start by diving right into the profiling results for VTM, VVEnc in the slower and the medium configurations. So basically, those are two comparisons. Let me start with comparing VTM versus VVEnc slower. So that's the orange bars and the light green bars. As you can see, we were able to improve the implementation of the VVC algorithm in VVEnc compared to VTM a lot, mostly in the intra-search, affine merge, basically affine search, also ALF. And all of those improvements, they come to VVEnc slower, running around 2 times faster than VTM. And bear in mind, this is at around the same compression efficiency. So this is 2 times faster on the one hand, but on the other hand, it's only 2 times faster. That's still not enough. And then we come to the second part of the comparison, that is VVEnc slower versus VVEnc medium. So it's based on the same implementation, but using different algorithm. Because of the different algorithm, we have a little bit loss in the compression efficiency, but the VVEnc medium runs 13 times faster than VVEnc slower, which is around 30 times faster than VTM. And the compression efficiency loss, it's totally acceptable. So, we arrive at this very attractive alternative trade-off, which is basically the takeout that I'm going to show you in this slide. And also it's kind of going to be the red line through the rest of the talk. Just improving the algorithm has much more potential than improving the implementation itself, but it has to be done in a smart manner. So how we go about, defining what algorithm to use at which step, I'm going to show you in the next slide. So basically at the core of VVEnc is the Pareto optimization, which is basically we put all of the options available in the encoder with regard to search. So like the coding tools we're going to use, the parameterization of those coding tools, and also the search algorithm variants that we're going to use for those coding tools into one big pot, and we try to derive the Pareto set, which is basically an approximation of the convex hull. So, it's the set of configurations that cannot really be improved. So we start by defining a starting point, which is a kind of an HVC-like configuration without any of the VVC tools. And then we step by step take the options from this, from this set of options, and iteratively define each next best working point. So we basically, on top of each point, we make a set of tool-on tests and see which option provides the best trade-off. On the right in the plot, you can see 2 Pareto sets. The green one is the one that we actually use, and for comparison, the orange one is a Pareto set created without accounting for the fast algorithm. So it's basically using the VTM algorithm, and as you can see, up until medium preset, we have around 2 times speedup between the two curves at similar quality levels. But after medium, the two curves kind of converge, which basically means from medium on in the faster curve, we're not really putting any more tools on top, but rather just removing the speedups and converging towards this VTM algorithm. Based on the Pareto set optimization discussed in previous slides, this is the presets that we arrive at. So as discussed, we have faster, which is a very HVC-like configuration with some of the VVC tools put on top of this and many of our fast algorithms. Interestingly, the VVC tools that we use at this point are all implicit. That is, they cannot be signaled per block. They're either on or off. And that's why they provide very attractive working points, because they do not increase the CU search space. Then through fast and medium, we enable more and more of the VVC coding tools. Also the coding tools that increase the search space, but mostly in our fast variants, that is with our VV-enc speedups. And then towards slow and slower, we gradually remove those speedups and enable the last 2 or 3 coding tools, basically converging towards the VTM algorithm and getting this last bit of gain. So in this slide, you can see similar information as in last 2 slides. It's basically the Pareto set in table form. And for each next enabled tool, you can see the respective working point. So basically, I want to repeat, what I said on the last 2 slides. As you can see at the beginning, we really have the new tools bring in a lot of gain, at very good trade-offs. So we don't have much runtime increase. And towards, after medium towards slow and slower working points, the new iterations, we only get those marginal gains, but at much larger runtime increases. So, the last bit of gain, it really costs a lot. That's why at the compression efficiency of VTM, we're only 2 times faster. In the last 2 slides, I showed you the VVC tools in the Pareto curve that is at their optimal working point. In JVED, the ad hoc group 13 has been tracking the performance of VVC tools, but based on the full VTM configuration, which is, let's say, not the optimal working point for most of those tools. So I want to show you a comparison of those. So let's start with the intertools, BDOF, the MVR. As you can see in VV-enc at the optimal working points, they have much larger gains. Of course, larger runtime because the baseline is much faster, but the trade-offs are better. This is because those tools, they cannibalize their gains a little bit. Further, for some intertools that do have per block signaling, like AMVR, MMVD, Affine, we were able to take most of the tools at a much smaller runtime by improving the algorithm. Further, the dependent quantization provides very similar trade-off in VV-enc and VTM, which is interesting because in VV-enc, it actually competes against a much faster baseline, the integer-based RDOQ. So this is nice to see. Also, the LFNST provides a much more attractive working point. We enable it way earlier. This is based by some alternative implementation. And then one more tool I want to point out a difference is ALF. In VTM, ALF, it's a tool that's not in the CU loop. So just because the CU loop in VTM is so complex, you don't see the actual overhead that ALF introduces. In VV-enc, we enable ALF pretty early in the Pareto curve, and you can see that on this really fast base, it really puts a lot of runtime on top. So this was interesting thing to see. And then as the last point, the MTS, there is an implicit version of the MTS, which basically cuts the CU search. And for us, it provides all of the gains at a much, much better trade-off. As an example, let me dig a little bit deeper into partitioning. So as you have seen in the Pareto set definition, for most of the presets, we use much more shallow BTT configuration. So we basically only allow non-1 or 2 recursive BTT splits. That is way less than used in the VTM algorithm, which allows 3 recursive BTT splits. And the VTM search algorithm for the partitioning, it was optimized for this working point of 3 recursive splits, and it really performs well under these conditions, but it doesn't really perform so well in those more shallow configuration. That's why we added some more heuristics. So on the right in the graph, you can see how those perform along the presets. So the green curve is all of our heuristics enabled versus the gray curve, which basically shows you how the presets would perform with the VTM algorithm. And as you can see, most of the time, the green curve really extends the Pareto set provided by the gray curve, except the last point. So basically for slower, we turn off part of our new heuristics, which basically shows you how, we start with all of those optimizations enabled, and as long as they provide improvement, we keep them on. But towards, when we want this last piece of gain, we turn them off when the Pareto optimality is no more given. See more details in the PCS paper. Thanks. Just as VVC, the Pareto set in VVENC is optimized for high resolution videos. So we derive our Pareto set based on the A1, A2, and B classes from the JVET test set, that is HD and UHD content. But of course, we want to validate that it works for different types of content, as you can see in those 4 graphs. So on top left, we have our training test set. On the top right, we have an HD and UHD validation test set. On the bottom left, we have low resolution test set. And on bottom right, we have screen content, which is basically classes F and TGM from JVET. And as you can see, the Pareto set looks quite all right across all 4 test cases, except on the bottom right, it has a slow bump behind fast. We're gonna have to look into this later, so that's an interesting thing to know. Otherwise, it really looks good, and the definition of presets is, it is very well done across the curve. Just for comparison, I also included the Pareto set as it was defined in the 0.2 version of the software. And as you can see, for low resolution as well as for screen content coding, it really didn't perform well. So, we're very happy that we were able to fix this issue in the 0.3 version of the software, actually. Next topic I want to talk about is the multi-threading in VVENC, which is implemented as a combination of CPU line and independent frame parallelism. Both of those approaches are combined in a single task-based implementation within a single thread pool, which means we schedule, different tasks that are all executed within the single thread pool rather than having multiple thread pools taking care of different kinds of workloads. Because of this approach, we have automatic load balancing, which in turn provides us very good multi-threading scaling, as you will see on the next slide. So basically, we have one task per CTU, and each task has to go through multiple stages. That's the CU search loop, and then the in-loop filters. That's LMCS, vertical and horizontal deblocking, SAO, and the ALF in 3 stages. And basically, the tasks, they synchronize themselves by, checking their dependencies themselves. And also some of the dependencies can be checked by thread pool, which kind of provides a little bit of a speed up. All right, let's see the results. This multi-threading approach provides very good scaling. For Fast and Faster, which use lower CTU sizes, translating to more CTU lines to parallelize, VVENC can utilize 20 and more cores efficiently. With Medium, which uses larger CTU sizes, similar as slow and slower, up to 16 cores can be utilized efficiently for UHD encoding. This approach comes with minimal efficiency trade-off, basically introducing around 0.5% bitrate increase over single-threaded encoding. And it can be further improved with additional options, as they do provide some additional bitrate increase. To conclude this technical part of the talk, the main takeout is VTM does not represent VVC complexity. And the coding tool performance, it can differ drastically depending on the context. So, it depends on the working point in which you measure a tool. It depends on the application scenario. It depends on the search algorithm. So in VTM, most of the search algorithms are designed to demonstrate full potential of the tool, meaning they are very verbose. And in VVEng, we have many alternatives of the search algorithm for every tool, allowing very different working points across the Pareto set. And just to give you two things to think about. One thing is implementation matters. So we were able to speed up VVEng versus VTM by the factor of 2 by just changing the implementation, but also algorithm and definition of optimal working points matter even more. And VVEng was from the start, designed with this Pareto optimality in mind. Okay, let's take a quick pause, and after the pause, my colleague Christian is going to continue with subjective optimization. Thanks.
Hi, I'm Christian, and my work at Fraunhofer HHI is mainly concerned with the research and development of algorithms which directly improve the visual quality of encoded videos. Well, why are such algorithms important? Traditionally, video coding is performed by optimizing a certain rate distortion trade-off, and that basically involves minimizing a squared coding error, which I'll get into detail later, for a given maximum allowable bitrate. And that's usually done independently for every picture, or in other words, frame in a video sequence to simplify this optimization. But ultimately, the receiver of the compressed video data is usually not a machine, but the human visual system. And if you read up about how the human visual system, or HVS, works, you find a lot of evidence that this system itself compresses the incoming data from the retina in order to avoid information overload. So basically what it does is something very similar to how we do video encoding. It predicts the stimuli that reach the retina, and then only considers the difference between this prediction and the actual data coming in. And these cues then are what is forwarded to the higher layers in the visual cortex. So when the target is human viewers, we should basically use some kind of perceptual rate distortion optimization instead of traditional optimization. This, of course, requires some kind of model of the human visual system inside the encoder's rate distortion optimization routine. Before we get into detail on how this model should look like, let's take another look at the traditional rate distortion optimization. So as the name implies, we have two variables, the rate and the distortion. And the rate depends on the partitioning, as we learned earlier, transformation and quantization, especially of the prediction residuals that are transmitted to the decoder. Usually this is done for a sub-area or block of a picture, or in case of audio coding, where this also applies, of a waveform. And the finer the quantization, the more resulting information, of course, and the higher the resulting bitrate. Typical distortion measure is the sum of squared errors, SSE, or the average of those values, which is called the mean squared error, or MSE. And the error here means the difference between the original and the reconstructed picture samples. And of course, the finer the quantization, the lower the distortion. So rate distortion optimization is a trade-off between rate and distortion. And the goal is to find an optimal trade-off given some maximum allowable bitrate, as I mentioned earlier, which can be solved or at least approximated appropriately by Lagrangian optimization. So essentially what we do is we determine the coding parameters for a given block such that the distortion plus some constant times the rate is minimized. The nice thing about this Lagrangian optimization is that it's very simple and it works well in block-based encoders. The Lagrange parameter, this constant that I mentioned, called lambda usually, can be obtained experimentally in advance, and then it can be fixed per picture. And block and picture independence can be assumed without sacrificing much of the possible coding efficiency. What would be nice, of course, is to keep this Lagrangian RDO approach, but to modify it to address perceptual considerations. So this distortion plus lambda r is an objective cost function, and it would be nice if we could turn it into a perceptual or subjective cost function. And one potential solution is to calculate, instead of the traditional distortion measure SSE or MSE, a visual distortion modeled after the human visual system. So ultimately, we would try to find an optimal trade-off between rate and visual distortion, which, as we could show in previous publications, can still be addressed by Lagrangian optimization. So to summarize, we would like to determine the coding parameters now such that visual distortion plus some blockwise constant times the rate for the given block is minimized. So what options do we have regarding the distortion measure? The simplest one is the MSE, which means we're optimizing for peak signal to noise ratio. The PSNR measurements are based on picture-wise MSE values, normalized to the bit depth of the assessed images, and for videos, usually the frame-wise PSNR values are averaged. The distortion is simply this, the difference between the reconstructed and the original picture data squared and summed up across a block or across the entire picture. Which means the distortion in each block contributes equally in the rate distortion optimization. There is no dependence on certain image characteristics, but when optimizing for the human visual system, there should be a dependence. As we can see on the right on this example, there are certain areas with bright illumination and quite a bit of color and detail versus some other areas which are darker and have little color and are smoother overall in texture. Such features, brightness, color, and detail, are related to luminance, contrast, and structure, and those are things that are addressed by the structural similarity measure, or SSIM, which averages, as PSNR does, picture-wise SSIM values across the frames of a video sequence, and for each frame it calculates a multiplicative combination of luminance, contrast, and structure similarity values, as shown here, which means that when optimizing and encoding for SSIM, the distortion for a block is inversely proportional to the SSIM value for that block. And the distortion in each block depends on the reconstructed and the original samples in the rate distortion optimization, which means since there are usually different SSIM values resulting from different areas of the picture, that each picture block contributes differently to the picture fidelity, which is nice, but the problem with this approach is that the computational complexity of calculating SSIM values during rate distortion optimization is higher than calculating simple SSE values, and therefore it's not so easy to implement in a real-world encoder. For completeness, I would like to mention two other options that are available for optimization. One is an improved version of the SSIM approach called multi-scale structural similarity, or SSIM, where the input and reconstructed images are downsampled and multi-resolution SSIM calculations are performed and later combined. In addition, there's the Video Multi-Method Assessment Fusion, or VMAF, that is currently considered one of the best ways of measuring video quality. It applies several video quality assessment methods, and the results of each of these methods or models are combined using machine learning approaches. The problem with those options is that the complexity is even higher than in SSIM due to the downsampling in case of multi-scale SSIM, or due to the calculation of multiple models and machine learning combinations in the VMAF approach. Also, the last time I checked, VMAF was not a differentiable assessment method, which means it's very hard to integrate into a rate distortion optimization framework. So with this overview in mind, here's a wish list regarding a perceptually motivated distortion measure. It should be easy to calculate with as few operations on the reconstructed pictures as possible. It should, of course, allow blockwise calculations, and it should be differentiable and provide high correlation with subjective impressions of visual quality. The solution we came up with is to generalize the MSE principle, known from PSNR, to a weighted MSE approach, which maintains the low complexity advantage, since we need to calculate only the SSE on the reconstructed pictures, and we apply a visual weight W of k to each block during the rate distortion optimization. So essentially we're using a weighted SSE instead of the traditional SSE. This allows us to determine the parameters such that the weighted distortion plus lambda times rate for a given block is minimized. To give you an overview of the technical questions that needed to be addressed during the implementation into VV-ENC. First, note that optimizing the weighted SSE plus lambda times rate is equivalent to optimizing the traditional SSE plus some adjusted lambda times rate, with lambda then given by lambda divided by the weight for every given block, meaning the distortion calculation can remain unchanged over the traditional PSNR optimizing approach, which is nice. The quantization parameter adaptation is then done similar to the lambda adaptation, specifically given an initial slice QP prime. We select the blockwise QP k as the QP prime minus 3 times log 2 of the weight and round it to the nearest integer. The QP prime is predefined by the given coding structure, for example, random access, and the given temporal layer of the currently coded picture. And we set the final slice QP to the average of the adapted block QPs to reduce the QP signaling bits. We also fixed the block size for the weighting to be easily alignable with the coding block sizes in VVC. So we chose a size of 64 by 64 for HD and smaller videos, and 128 by 128 for UHD videos. We further implemented a simplification in VV-ENC where the block size for QP adaptation is always 128 by 128, meaning the CTU size in interframes, since a final resolution of the blockwise weighting was found not to lead to better visual quality, and it complicated things a bit in the search loop. With those objective things considered, the question remains, how should we choose the W of K? Well, the most important part is a simple model of spatial and temporal visual sensitivity, because spatial sensitivity within a given picture, that is, and temporal sensitivity, that is between pictures, tells us something about the masking properties for the given content. We largely disregard frequency sensitivity, which is another aspect of human vision, because that's highly viewer and environment dependent. So we get sample-wise visual activity values, which tell us something about the spatial and temporal masking, and then average these values across a given block. The measure of spatial sensitivity can easily be realized by spatial high-pass filtering, for example, Laplacian of Gaussian filtering, and that acts as a kind of edge detection, as you can see on the right. The measure of temporal sensitivity is analogous in temporal direction, so it's a temporal high-pass filter that works well here, which is some kind of simple motion compensation, and also, in other words, a kind of temporal edge detection. It identifies the largest differences between subsequent pictures. This simple spatio-temporal high-pass approach is the foundation of the so-called extended perceptually weighted PSNR measure, or XPSNR, that we devised during the last few years. It defines a blockwise weight WK as follows, depending on the image width and height and bit depth, where a pic is an average value determined across a large set of videos, and A of K is a visual activity measure using the previously mentioned spatiotemporal high-pass to obtain a measure of the sensitivity or masking capability of a given image area. The definition is as follows. It's the sum of the absolute values of the spatial high-pass output and the absolute values of the temporal high-pass output squared and limited such that lower values are clipped to some minimum value. Note that these formulas only contain low complexity operations because the squares and the square roots largely cancel. So, the best way to check if the visual quality has improved due to our perceptual RDO is to perform visual tests with a large number of viewers. And actually, during the finalization of the VVC standard, a subjective test has been conducted with VVEnc and the VVC reference software VTM included. And VVEnc ran with visual RDO based on the XPSNR model just described in preset medium. And the environment was a controlled one in 2 labs with a certain OLED TV setup. And 2 tests were run, one with UHD content and one with HD content. The first one with UHD content in random access SDR configuration comprised VVEnc 0.1, so a very early version of VVEnc, with motion compensated temporal filtering enabled and VTM running in version 10. And the results, as Adam already showed, and shown again here in the upper figure, indicate that VTM is outperformed by VVENC with the perceptual optimizations at mid and high bit rates. And in the second test, done more recently with HD content, VVENC 0.3 was being used and VTM 11, and both VTM 11 and VVENC used the MCTF pre-filtering. And there, again, the same result. VVENC tends to outperform VTM at the high rates. So we have two tests available, and the results are a strong indication that the visual optimization in VVENC does what it's supposed to do. Nevertheless, we wanted to know whether the XPSNR model would also work on larger data sets, and especially if it would be useful as a full reference video quality assessment method. For that reason, we tested the XPSNR performance in predicting mean opinion score data on several publicly available annotated datasets. The performance was quantified by mapped Pearson linear correlation coefficients, which model the linearity of the correlation, and Spearman's rank order correlation coefficient, which models the monotonicity of the correlation. The tested content involved 9 public DMOS annotated datasets, which are listed here. And the methods that we included for comparison are those which are, in terms of computational complexity, comparable to XPSNR, and for which C or C++ source code is publicly available. And those are the ones that we were able to collect. What I show here on the right are the Spearman results from our 2020 ITU paper on XPSNR, which is publicly available, and I highly recommend you take a look at this reference if you want to know further details of the XPSNR implementation or its performance. And to answer the previous question of whether XPSNR is useful as a VQA method, yes, it is. Apparently, because overall the correlation numbers we get across the various data sets are slightly higher for XPSNR than they are for SSIM or VMAF. What's not included in the ITU paper is the CSIQ subset, so here are the results including that subset. The results are very similar. XPSNR comes first with a Spearman correlation coefficient on average of 0.83, with the other VQA methods around 0.82 to 0.80. The mapped Pearson results are very similar. There the VMAF scores second instead of third, and the SSIM and MS-SSIM methods share third place instead of second place in the Spearman results table. I'm planning to update this evaluation with the results of the more recent JVAT verification test results that I previously showed. But for now, I'll leave you with the conclusion that the subjective optimization in VVENC seems to work. Thanks for listening, and I will hand over to Ben again.
Thanks, Christian, and hello again, everyone. Let me wrap up this workshop with an outlook and the conclusion. So the work on VVC continues with the open implementation VVENC. This includes further reducing the complexity. Main focus of further work is exploring how to use neural networks to assist the VVENC in decision making, for example, for partitioning, inter-motion search, mode decision, and so on. to further improve the coding efficiency by adding a content dependency with some pre-analysis to determine adaptive GOP length or referencing structures, as well as an adaptive frame level QP cascading depending on the content. We will further pursue integration into multimedia frameworks such as FFmpeg and GPeg, so you can use it in multimedia environments. So stay tuned for further updates on GitHub that we will release on a regular basis, and also stay tuned for the papers that we will publish on that in the future. To conclude our workshop on VVC open optimized implementation with the VVEnc as one example of a freely available VVC encoder implementation, it provides high compression efficiency at very fast runtimes. This is achieved through software and search algorithm optimizations. This includes Pareto optimal tool settings, resulting in 5 performance presets, trading off coding efficiency and runtime, an efficient, scalable multi-threading approach that also takes care of keeping up with the high compression efficiency. Then for subjective quality optimization, which is a main part in VVEnc compared, for example, to the VTM reference software, Christian explained how the block level, low complexity perceptual rate distortion optimization works using the XPSNR measurement. The experimental evaluation was shown that indicates the effectiveness of that XPSNR based RDO. And as shown in the VVC verification tests, VVEnc in its medium preset with that XPSNR rate distortion optimization and error control outperforms the VTM reference software with PSNR based RDO in visual quality. So thank you for your attention. We hope we have been able to give you detailed insight into these 2 aspects of VVEnc, and we are further available for questions after that video. Thank you very much.